Hello and welcome to the course Design Borefields with Confidence. This is the first chapter of this third part, and we will be talking again about monthly and hourly temperature profiles. Now, in the last part, where we started with our first geothermal simulation, we also talked about hourly and monthly temperature profiles, but from a more high-level viewpoint, let's say, what we can learn from them. Now, part 3 is all about making more accurate designs using state-of-the-art methods, which will be discussed in the chapters to come. But in this first chapter of this part, I want to focus again on the difference in accuracy or in insights you can get from using hourly versus monthly temperature profiles. And just to recap what we already talked about earlier in this course, in GHG Tool you can either work with monthly load profiles, typically in feasibility studies where we have the energy and the peak powers for every month in the simulation. Or you can work with hourly load profiles, like the ones here on the slides, where we know from, for example, a dynamic building simulation. So we have simulated our building in another software, and we know now for every hour what the heating demand is, what the cooling demand is, and what the domestic hot water demand is. Now in this example, which is for a residential building, you can see that our domestic load is constant. The load for domestic hot water is constant. Normally, this is also some tap profile, especially for swimming pools or hotels, buildings with quite a lot of domestic hot water demand. But in this case, you don't know when the domestic hot water will be, so we just assumed it to be constant, so it only contributes basically to the imbalance. And this is, for example, an hourly profile. Now, to illustrate the importance or the insights you can get when working with hourly when compared to monthly load profiles, we are going to simulate two buildings in GHG Tool. One residential building, and you saw the hourly profile before, which has significantly higher heating than cooling demand, also quite a high domestic hot water demand. And on the other hand, we have an auditorium building, which has not a lot of heating, but quite a high cooling power. So two completely different buildings, which will lead to two completely different temperature profiles, and we can learn different things from both of them. So let's jump into GHG Tool Cloud and show you the difference when we design both systems with either the monthly loads or the hourly loads. So here we are in GHG Tool Cloud, and as you can see, I already created 4 different scenarios, 2 for the residential and 2 for the auditorium building. Now, if you want to try recreating these results yourself, all the required input information is over on our textbook. And if you scroll down to the end of the chapter, you will see everything. You can download it there and recreate what we will be doing now yourself. But just as a brief summary, we have temperature limits of 2 and 17 degrees and simulate for 25 years. Our ground properties will be constant, it will be the default values. For a residential building, we have a bore field rectangular of 7 by 4 boreholes, 150 meters borehole depth. A borehole resistance in this case will be a W tube, monopropylene glycol 30% volume percent, and we have a flow rate of 5.6 kilograms per second for the entire bore field. And then finally here, the star of the show is our thermal demand. So we have a 60,000 kilowatt hours per year. You can also enter it in megawatt hours if you want that. And we have here our monthly loads, peak power, and yearly energy demands. So if we simulate this, we see here our numerical results. As you can see, our minimum temperature is quite above our 2 degrees limit, but we are close to our maximum temperature threshold of 17 degrees for passive cooling. So if you look at this temperature profile, one would say, okay, we have a significant imbalance due to the heating and domestic hot water demand. But actually this borefield is designed here in this first year for the passive cooling. Now, one could argue, well, due to the imbalance, we do not really care about this first year. But the thing is that in this monthly simulation, if we would zoom in, this is quite just too much. So here you see it's almost 2 months that we're at this threshold. And you do not know if this threshold will be met 1 hour of the simulation period or 2 months in total. So that's the problem with the monthly simulation. We clearly are limited by the maximum temperature limit, but we do not know how critical, let's say, that limit is. Now, instead of working with monthly load profiles, if we go to the second scenario, what I did is I just downloaded the hourly load from my building simulation software and I uploaded it here. Still kept my 60 megawatt hours per year of domestic hot water demand. And over on our results tab, we now see a totally different story. So here our maximum limit is significantly below our 17 degrees, and we're actually way closer to our minimum limit. So in both cases the design was correct, but due to different reasons. And that's perhaps a little bit strange. And the reason for that is in this strange parameter, let me go back, this peak duration. Now, if you have an hourly load profile, you don't need this peak duration, and we already talked about that. Because if you have an hourly load profile, you know exactly how long the peak duration is in both heating and cooling, because you know the load at every hour. But for a monthly profile, yeah, you just say, okay, in this month we will have a maximum heating and cooling demand of that amount of kilowatts, but you do not know if that's for 10 hours or 1 hour or perhaps a whole week. So that's why we need this estimate, this mathematical concept of a peak duration, which is best described as being, okay, if our heat pump turns on at maximum power, or the maximum power of the month, how long will that power be there continuously? Now, of course, this is a sort of estimate because you cannot really know how long it is. So it's just to fill in the gaps, because you have no hourly profile, to fill in the gaps to move towards making a simulation with a monthly profile. And typically it's between, let's say, 2 to 16 hours or something like that. It really depends on your building. For example, without going too much in detail, if you know that you have a very low slow emission system, floor heating, concrete core activation, and so forth, typically your peak powers will be lower in absolute value, but they will take way longer. It's a slow emission system, so you will have quite a constant flow of energy. So that's just a little bit how you can reason about it. Now, the problem is that you do not know in advance what the correct peak duration is, because now we could say, okay, we have here our hourly load profile, and if we zoom in, for example, in this last year at this minimum limit, you see here that, yeah, there are quite almost 4 days, 3-4 days, where we meet this temperature minimum limit. So perhaps our 8 hours for the peak duration of heating is an underestimation of reality. But we only know that a posteriori. Now we know that because we have the hourly data, we simulated it, so we know, okay, we have quite a high heating demand, especially during a couple of days, but we do not know that with our monthly loads. And the same story is actually true if we go to our first year and we zoom in on the cooling demand. So here we have a maximum day, the 10th of August in this case, and we see that we only have a couple of hours where our peak value is at that high temperature. So probably 8 hours for cooling here is, yeah, again, a little bit an overestimation. And now one can try to find the correct hourly or peak durations to make the monthly simulation match our hourly ones. And perhaps it's interesting as an exercise to do so. In fact, let's make an exercise out of it and let's try that for yourself. But this is only something you can do a posteriori when you have this type of information. Now this is for the residential building, where we say, okay, our design still is the same, in this case, at least, but the reasons why it's designed in such a case, they differ. in monthly profile it was for the maximum limit. In hourly, the more accurate one, it was actually for the heating. Now if you go to our auditorium simulation, you see we're way above our minimum limits. It will not play any role, but we're here strictly limited by our maximum temperature. And we also have a bore field in this case of 36 boreholes to cope with this passive cooling limit. And again, here you do not know how many hours we are at this maximum level, but we know that, yeah, in an auditorium, cooling is quite an important aspect of your thermal comfort. But if we would go to an hourly simulation, what we see is that we are significantly below the 17 degrees. And we're at 16.19 degrees. So if we just zoom in, you see here that we have a very peaky profile. And that's because, to give you some insights, this auditorium was simulated with floor heating. But because, yeah, the auditorium, it fills itself immediately with people heating up quite fast. So the cooling is all air. That's why we have quite a high cooling demand, cooling peak, not on a yearly basis, but the peak demand is quite high. But you can see it just for a couple of hours. In this case, the value is only met during 1 hour. So you can see that saying it's for 8 hours, it's total overestimation in this case. And in fact, let's us duplicate the scenario and let's see if we can make this bore field smaller. So let's make a smaller bore field. Let's go to the bore field and let's make it a third smaller, shall we? So we go from 9x4 boreholes to 6x4 boreholes, cutting away 33%. And in our results, yeah, we see, okay, we're now way above our 17 degrees limit. But since we have an hourly simulation, we can actually zoom in and see, okay, how critical is that? And as you can see here, yeah, we cross our limits, but it's only, let me check, 1 hour of the simulation period. And the peaks and the hours below, we are already below the 17 degrees. So in this case, you could argue, well, we can work with 24 or perhaps even 22 boreholes. Let's say because, yeah, we cross our limit, but it's only during 1 hour and we have a very high resolution because it's hourly. But this does not mean that this hourly profile is actually the truth. It really depends on what weather profile or what occupancy profile you use for your dynamic simulation. So to end this summary, because you can see we just avoided a significant oversizing, it's really important that you understand your hourly profiles. What's behind them? Do you understand how they were created? What assumptions are behind them? And do you trust these simulations and these results? Because if you do, and it's an accurate or a trustworthy simulation, using hourly data in a tool like GHG can actually help you make way better bore fields. And also, as you will see in the next chapters, also use more of the advanced models, state-of-the-art models, to make even more accurate geothermal simulations. So this just to show you hourly, monthly, it's not just a different type of information. You can really get better designs out of it if they were created in the correct way. And as we will also see later in this course, if you don't have hourly data, you can actually create it within GHG yourself. But that we will cover later in this course when we talk about simultaneity. So I hope I already convinced you that there is value in hourly load profiles. Now let's see how we can improve even more on the geothermal design when talking about variable fluid properties in our next chapter.